Good afternoon. So everybody is excited about the midterm tonight? There will be only the lectures between Monday, the day of midterm 1, and Friday will be part of the midterm. Everything I tell you today will be part of the next midterm. Okay, did this answer your question? I said this many times actually, all right? So let's do it. Let's just get right into it. We have been talking about pressure, volume, and temperature, and we have talked about these macroscopic properties. So we have seen that pressure and volume is a constant, and pressure and temperature relates to each other, is proportional to each other, and the pressure relates to the number of atoms that you have. The more atoms they have, the higher the pressure is. And so these laws we have then united to the ideal gas law. P times V is N times R times T. And today, I would like to take a little bit closer look how we get to this macroscopic observation. Now we go back to the microscopic and look at each molecule and see how we generate that pressure or that temperature in a certain volume. So we're using the kinetic theory of gases. And there's a couple of things we need to know about the ideal gases before we can apply this kinetic theory. The first condition is that the gas consists of identical and well-separated particles. So actually, particles in the volume, they are very few compared to the size of the volume. So a mole of particles is a lot, but if you have a liter, it's not a whole lot. There's lots of empty space, actually. So we're looking at the number density of these particles, of the gas particles in that volume, and number density, for example, in population density. I would say the number density of the population of Montana. There's lots of empty space, okay? There's not that many people living in Montana. And if you compare this to the number density of people in California, that would be not a very good example for the kinetic gas theory. So they are very far apart, these individual gas molecules. They do move in random direction all over the place. They move, and with this they have a direction, a distribution of speeds, okay? So we need to find some kind of an average speed in order to describe this. And then they collide with each other. They collide with the walls and they collide with each other. And when they collide after the collision and before the collision, they move in straight lines. They don't go zigzag, okay? They move in straight lines between collisions. And the collisions between the particles or the walls, eventually we want to determine the pressure on a microscopic level. They are elastic, these collisions. They are inelastic collisions and elastic collisions. Those of you who listen to physics, you know elastic collisions, there is no loss of energy at all. So the energy gets transferred within the collision. So there's the conservation of energy, but inelastic collisions, you lose when they collide particles with each other or particles with the wall. Some of the energy is given off as heat, for example, to the wall. We don't have that. We have elastic collisions, all right? So this is now we have set up the conditions for our model, and now I'm going to give you sort of a little bit of a pictorial understanding before we go and do some heavy lifting, and we're going to derive the kinetic theory of gases. And I've given you within the handout, I've given you some handwritten notes from me, and they should help you a little bit. So if you have an ideal gas, it's all about the momentum transfer on that wall here, okay? That's what is the pressure, what causes the pressure. And so in order for you to understand momentum transfer a little bit better is, so the molecule bounces, so the atom bounces into the wall and bounces back, and this is an elastic collision. And so some of you probably have kids already, or many of you have little brothers or sisters, or you've been invited where kids are, and there's these toddlers down there on the ground, and you stand there and talk to somebody, and So the toddler has a little toy car, and he plays with the toy car and hits you on the foot with the toy car. You look down and say, oh, okay, not much happened here. So that would be not the right example. The other example would be, for example, my hand. My hand has always the same mass. And if you have somebody who is not thinking very well about you, you would do this. That would be not very effective because you don't transfer a lot of momentum. Momentum is mass times velocity. Okay, the mass is the same. If I have slow velocity, I'm not transferring some momentum. I would need a huge hand and move it that small. If I move a huge hand, then I would transfer that momentum. But I only have one hand, okay? And you want to have, if you want to exert pressure, you want to have a very small area, okay? Pressure is force on area. That's why when you hit the chin, the area is very, very small. That's what the boxers try to do. They try to hit the chin. Some people call them, they have a glass chin, actually. And so you hit the chin. I'm not suggesting this at all, okay? But if you do like this, okay, then it might cause a lot more harm than if you do like this, because the mass is the same, and I transfer a lot more momentum or pressure on that chin, okay? So that's the first thing. Now let's go, that was the first momentum transfer. Now let's go to that other. Here I'm standing here at the cocktail party where they have these little kids running around, and so this hits me with a car. Little car hits me, and so not a whole lot of momentum transfer. But I also, some of you have seen me probably, I take the 51 bus in the evening sometimes, and I'd be very careful because this thing is big, okay? And it rolls there when it rolls into the station, and I'd be very careful not to get into it, into its way, because there would be a huge momentum transfer onto me. That would be something like this here, okay? And with this, that would be the end, for me at least, for this semester of Chem 1A, all right? Never know, man. Don't hope for it, okay? And so this is about momentum transfer, all right? So we need to do this a little bit more scientifically, but you get the idea that large particles move slower and small particles move faster to transfer the same kind of momentum. All right, and now we're going to look at this a little bit more, and we're going to look at this gizmo I have over there, Elmo, and if you can take out the page that I gave you, it's exactly what I'm going to talk to you about, or going to derive for you. So can we have this up there, please? Excellent. And you tell me, please, sir, you tell me if I'm talking, but you don't see it up there, because I need to move the paper. All right? So I'm getting so excited about all this stuff that I keep talking and you don't see even what I'm pointing at, because it's not there. So we want to discuss the microscopic origin of pressure. So we know that the force is mass times acceleration. Mass times acceleration. So what is the mass is given, and acceleration is the change in velocity in a certain time, in a change of time, okay? What is my mass? This mass is m, okay? Now I look at my box here. So this is the wall of the box, and this is the length of the box. The particle travels along here, hits the wall, and then gets bounced back elastically back into that box, all right? So what am I really interested in is, when does this happen again with this one particle? So that means it is, so the direction of this here, this is 2 times Vx. So it goes in and out. So this is, the velocity is 2 times Vx. And now I want the time between the collisions. That's the frequency, how often this happens. So the frequency is the length goes in and out, 2 times the length, divided by the velocity. All right? So now I have this equation, and it says F equals m times 2 times Vx divided by 2L, and this is divided by Vx. So now I bring this Vx up here, the 2 I can cancel. I bring this Vx up here. Now I have Vx squared, okay? And divided by L. So I have the force is m times Vx squared divided by L. This is the force for one molecule on that wall here, okay? So, but I have more than one molecule. And I want to discuss this in terms of a whole mole. Okay, so I take a whole mole of it times m divided by L. This is fine too. But my velocity is now not the velocity of this one particle. You have an average velocity, v bar. Okay, and you square that. That's the average velocity. With this now you have that force is n times m times v bar squared in the x direction divided by L. All right? So, but we are wanting not the force, we want the pressure. So pressure is force per unit area. This is my unit area here. Okay, here's the wall here is my unit area. So force per unit area. Okay, I have the force I just calculated, n times m times v bar squared, divided by L. Okay, and L times A is the length here times this area. That's a volume. I can write V here. So now I take that V, it's on this side, I take this up here. I have the V is on this side, I take this up here, is P times V. And now we have to introduce something for the average speed. So the average speed for 3 directions is nothing but 1/3 V bar squared. Okay? We had this, in order to express this in terms of the total distribution of speeds, we say 1/3 this here, we put this in here, and so we have then P times V, we have P times V, is 1/3 times N times M times V bar squared. So now we have linked the pressure times the volume. What was that? Boyle said pressure times volume was what? A constant. Now there's our constant right there. You have the constant now. So we link the microscopic properties, the macroscopic properties to the microscopic. Actually, they are not microscopic, they are nanoscopic. We know that these molecules are in the size of nanometers and smaller. So microscopic is actually an old word. We should say nanoscopic properties. And so this is P times V is 1/3 times N times M times V bar squared. So that's the average velocity. So now we want to find the microscopic origin of the temperature. So we just did this here. P times V is 1/3 N times M times V bar squared. But we also know from the ideal gas law that P times V is N times R times T. Okay? So the physicist amongst you can do this in your sleep probably. That's why I'm showing you this actually. I don't expect this that everybody will, if I wake you up at 3 o'clock in the morning, that you will be able to derive this for me, okay? But you should get an idea about this. So this here, I can equal this now. So this I have, 1/3 NmV squared. This is my microscopic observation. And this is N times R times T. I have that here, N times R times T. So now I rearrange that, and I rearranged it to get this V bar square here. So I have to multiply this by 3 to bring this over here. Bring this N down here, okay? Bring this M down here. N times M is the total mass, isn't it? N, the number of molecules I have, times the mass per molecule, the molar mass per molecule. So I get this here, and now I divide by N, the number of moles I have. With this, I get the molar mass, okay? So what this says here, V bar squared, or this is the average squared velocity, is 3 times M times R times T. So what does it shows you, and now I can do, this is the question here, the equation here, V bar squared. Now why don't I bring this M right over here, okay? And now I just expand this with 1/2. If I have 1/2 M times V bar squared, what is that? Thank you. 1/2 times, I expanded this. I had this equation here. I rearranged it. I expanded it with 1/2. So I have 1/2 M times V bar squared. What's that? That's the kinetic energy. Okay? And this is 3/2 RT. And this is per mole. So the kinetic energy of 1 mole of ideal gas, any gas essentially, is 3/2 RT. Do you see any mass in there? No. The kinetic energy is directly proportional to the temperature. R is the Renault constant, and T is the temperature. So there's your equation for 1 mole of ideal gas to determine the kinetic energy. Now, if I'm going to introduce you now to a new constant, if I have R divided by NA, R divided by NA, NA is the Avogadro constant. So what is this? This is the energy per 1 molecule or per atom, all right? So I call this Kb, a new constant. It's just R, the Renault constant, divided by the Avogadro's number. And this is 8.31, and this is joule per Kelvin per mole, divided by 6.023 times 10 to the 23rd per mole, okay? So what does it give me? It gives me an energy in joules per Kelvin, and this is 1.38 times 10 to the minus 23rd. That's the energy for 1 gas molecule, okay? So what does that mean if I look at this equation here, or this equation for 1 molecule? That would be the average kinetic energy is 3/2 Kb times T per molecule. That means cold molecules have less kinetic energy, they move slower, and warm ones move much faster. And you've seen this when we did the balloon experiment where I took the balloon and put it in liquid nitrogen. So suddenly I exerted much less pressure because the kinetic energy went down. It's just a function of temperature, directly proportional to, didn't have to do anything with the mass at this point. And if I would have put this in hot water, the balloon would have become bigger. I only choose to put it into the liquid nitrogen. Remember, I put the little doggy in there? Same thing, was still a balloon, a Fido, okay? So now we did a little heavy lifting, and we gained some equations from this, and the equations that we gained are the ones that we're going to use, and I wanted to show you how I derived those. So P times V, that's what I just did, all this stuff here. So the kinetic energy per mole is 3/2 RT, all right? No mass in there. It's just proportional to the temperature. And the average kinetic energy per molecule is 3/2 times the Boltzmann constant. And I tell you at another time, I'll tell you a little bit more about Boltzmann, very interesting story. The Boltzmann constant times T, and the Boltzmann constant is R divided by Avogadro's number. So that's the constant for 1 atom or 1 molecule. So these are the equations that you need to know. And yeah, we could put this, okay, fine, all right, good, let's not be choosy here. So I'm going to ask you a question now. Remember very carefully what I told you. What was that? This one I showed you here. I put this up here because now you can read this. Let's put this up here, please. The right screen, if you could, please. So I show you this here. This is all you need to answer that question. So I have 1 mole each. Looks very strange, actually, if you think about it. I have 1 mole each of bromine and hydrogen, and I place this in a balloon. What are their relative kinetic energies? So obviously the temperature is the same. So is the kinetic energy of the bromine larger than of the hydrogen molecules? The bromine the same than the hydrogen, or the bromine smaller than the hydrogen? C is bromine smaller than hydrogen. Here's the rest of it, okay? All right. So why don't you think about it and give me your answer, please? Where's my coffee? Oh, here. So I gave you the mass here of hydrogen and bromine, okay? Yeah, there is a Gaussian distribution. And why don't you discuss this with each other? So I went through all this to show to you that the kinetic energy depends on 3/2 RT, okay? And I said, and suddenly I give you some masses. Doesn't make any sense to me, actually, okay? So why don't you discuss this with each other and give me your answer? Come on, discuss it with each other. You need to know this for midterm 3. Oh, midterm 3. We barely have done midterm 2. What is it? I went through all this, it only could be B. It doesn't matter, you need to understand it. It's not being right on your clicker, you have to understand it. If you don't understand it, it doesn't really help. Okay. So now let's see that result. Huh? Look at that, huh? Isn't that something? It's phenomenal. Absolutely phenomenal. Where's my right thing here? There it is, okay. That's green, okay. I derived it for you. I said that the kinetic energy of these gases, in fact, ideal or any gas actually, if it's not too hot, depends only on 3/2 RT on the temperature, directly proportional to temperature. Now think about it. The larger molecules will move slower, and the faster will move, the smaller will move faster. That's what it is. That's how you get this dependence only on the temperature, okay? And not on the mass in this case. So let's have a look at this. Kinetic energy depends only on T, okay? And with this, the answer was, let's see, yeah, this is what I have shown you here, but this is what is equal, and this was, you probably fell into that here. So with this, the answer was B, as all of you had so fantastically right, all right? So now we have this, we talked about this, where is it? This speed here, that mean square speed. You can't really use it for anything. I don't know any. I don't run with the mean square speed, okay? I run with a speed, a root mean square speed. That I could do. So you have to have some kind of a speed, but not a square speed. And the root mean square speed is, this is the square, and I have derived this here. This is the mean square speed is 3 kb times T divided by m. And this is 3 RT divided by m. But I don't want the mean square speed, I want the root mean square speed, okay? The root, if I take the root of this, then I get VRMS. That would be, VRMS would be the root, so I have to take the root of this, and the root of that, and with this now I have a speed that we can do something with. We call this the funny name, the root mean square speed, okay? And for ideal gases, the root mean square speed is 3 RT divided by the mass, the molar mass, and this is the square root of it, or the temperature, so it's directly proportional to the temperature, to the square root of the temperature, and inversely proportional to the mass, okay? So this is, I think this is the next one. It's given to you here in this panel. You might need this for one of the following questions, or one of the at least following questions. So we have defined now the root mean square speed. We just took the root out of that the mean square speed to get the root mean square speed. Okay, the root mean, the root mean square speed is proportional directly to the root of t and inversely to capital M, all right? So let me give you a question. Now there's a lot of pumping going on here, huh? So to speak. So the root mean square speed here is if we plot that here, and I get this straight line, what do I have to plot here on x? Do I have to plot the temperature squared, the temperature, or the square root of the temperature to get that line? So that's a linear equation. Everybody should know that. If you could please put this here, this panel, the left panel, up there. Excellent. Thank you very much. So think about it and give me your answer. You should be able to answer these kind of things by now, halfway into Chem 1A and halfway into physics and halfway into math. What kind of math are you taking? 54 or something, or 16? 16, okay. Who's taking math 54? Oh, excellent, okay, good. Not 54, 2 years ago, okay. All right, good. And the others take 16? Okay, you had linear equation there already, the equation of a line? Yeah, good, excellent. And you know what the linear equation is? The other day, I got an email from a professor, one of my colleagues. There was a student who went to my colleague who has nothing to do with Chem 1A and asked him, which is fine, about that person didn't know what a linear equation is. But we have all the GSIs. They can come to my office. They can read in the back of their manual, actually, and there's about linear regression something written. And who knows how to do linear regression with don't forget to click in. Who knows how to do linear regression with Excel? Okay, did somebody teach you this in this class here? I mean, the GSIs taught you? Okay, that's important. So it's not about Flickr and iClicker and whatever. It's about using programs, all right? If you can manipulate your phone, you still can't do anything, all right? So you need to learn how to use decent programs. So and I always am under the impression that the young people, because I'm amazed how people are doing the texting on their phone. Like this here, okay? So I said, they can text like this. This is fantastic, these guys, you know? And then I said, they must know everything about computers and everything about using programs. And then I found out they can't use Excel, all right? So that's, I mean, it's just a little bit exaggerated, of course, but many of you know Excel. But it would help to know that. So let's see what the answer of this was. Wow, see? Pretty good, actually. Pretty good, pretty good. So that is, of course, a equation. It's got to be linear equation, got to be over t, square root of t. And with this, I'm going to show that to you. Okay, if this here is the root mean square speed, is the square root directly proportional to the square root of t, you wouldn't get a line like this if you wouldn't plot square root of t here. Okay, good, excellent. Now, I'm not berating you, please don't misunderstand. I admire you, how well you do texting, especially while driving, you know, or eating, or talking, you know. But you need to also learn some decent computer programs, okay? And many of you have done that. So, I'm going to have a race now, and I'm going to race bromine. Bromine is a brown gas, and why I'm doing this, the reason why I'm doing this is I want to show you the speed of gases. Okay? And I'm going to beat bromine in its speed. What I will do is, or we will do, Karen will put in here bromine, it's a brown gas, And you heard that she evacuated that line. There's nothing in that line, okay? So, and then she will open a valve here and open the vacuum. Oh, she will open the valve over there. Then that gas will travel from here through that line to here. So you can see the gas. If you look very quickly, you can see the gas traveling. And I will raise the gas, okay? All right? So I used to be a soccer player, and I was pretty fast, actually, relatively. At my time, they had still clay tracks, you know. They were pounded clay. And so I used to run in my tennis shoes or something. I always did 12.8 or 13 or something. And then this one guy had these spikes, you know, with these running shoes. They had these spikes on there. You don't use this anymore because you have different surface. There's some different. So I put those on. They barely fit, so I put them on, and I raced, and I was 12.3 immediately. Okay, I didn't have any spikes, so I didn't try them anymore. I said, okay, 12.3, not so bad. The world record was then 10.0. It's now 9.61 or something. The world record for 100 meters. I was talking about 100 meters. So this is not quite 100 meters, and we have the bromine. Can you see the bromine here? Very nicely. You see me? Fit? Okay. And so I have to stretch a little bit, actually. And all right. So I'm going to have a race, and you're going to watch me, but also watch the bromine, how it comes over there. And then tell me who is faster. I'm going to be faster, of course. Yeah. And so let's see. Am I ready? Yeah, let's see. I'm ready. Oh, no, not really yet. So, ready. Count me down.
2, 1.
Does they say, go? It is. Okay. So I lost already. Okay. But they didn't send me. Okay. They said 1 is not start or boom or something like this. All right? So did you see how fast that gas went in there? There's no way that I beat that gas, okay? So, but I would like you to show how I can run, but it didn't work. But you've seen that there's no way. If I do, let's see, I do maybe 100 meters. If you do it in 10 seconds, you do 10 meters per second. So I probably would do 5 meters per second, okay? That at my age, 5 meters per second. It was pretty fast, actually. And so that gas is much faster than 5 meters per second, okay? So with this, I'm sorry you didn't see me run, but because they didn't send me. Oh, now I'm really sad, okay? Okay, all right. So now, there is the experiment. There's the experiment, and you see here, what is the root mean square speed? That was the speed you've seen for the gas going from here to here. In meters per second. For bromine, okay? Bromine is atomic mass is, let's say, 80 grams per mole, okay? 80 grams per mole, and let's say it's 300 Kelvin in here, all right? 300 Kelvin in here, and I want you to calculate what the root mean square speed about, just to estimate it, of that gas is here. Is it 1 meter per second? Is it 10 meter per second? Or is it around 100 meter or larger per second? So why don't you think about this? You need to put in a couple of constants and then give me your answer. There we go. This is the root mean square speed, okay? So the temperature you have given the mass. Remember bromine, how many atoms form one molecule? How many atoms? How many atoms form one molecule of bromine? 2, thank you. Who was that? Who said 2? Good. Everybody, all right, the guy right there. So exactly, so it's Br2 obviously. So that's the mass then, the molar mass. And the temperature you have, you know what R is, but there's the mass, there's a trick there. You have to put it in kilograms in there. Okay, let's have a look at this. Well, that's to be expected. It's not an easy question. So we know, obviously, this equation here, okay? So you have R is about 8, isn't it? And T is 300. And 3, this is 3. What's M? M you have to put in kilograms. Why is that? Because a joule is a square meter per square second times kilogram. Okay? You have done this in your homework, didn't you? Stuff like this? No? So put it in kilograms. So, and then calculate it and give me your answer again. Why don't you discuss it with each other? Next time when I do this run, I need a starting pistol, okay? I'm going to bring a starting pistol. That way there's no misunderstandings or false starts. Actually, the gas had a false start, okay? But it's kind of difficult to get it back into the bulb over there. So is it 1 meter per second, about 10, or maybe about 100, or even bigger than that? Yeah, C is right. Actually, it's 200, over 200, and I'm going to show you why. So this was our equation, and with this we have 3 times 8 times 300 divided by 160, but we have grams, now we have to have kilograms, times 10 to the minus 3. So how can we do that, okay? This here is about, what is that? That's about 2, a little bit less than 2, okay? That's about less than 2, and so this would be 2 times less than 2. Let's say this is 2 times 8 is about 15, huh? 15, and this 10 to the minus 3 we bring over here, that's 15,000, okay? Times 3, about 45,000. Anybody can punch it in what 45,000 is? Square root? 212, actually, and the exact number is 216 meters per second. And with this was the closest and most right answer. So these gases are tremendously fast, all right, even at room temperature. And they're getting faster as higher the temperature goes. And now we're talking about the distribution of speeds. The distribution of speeds this is a distribution function of your speed here. If you plot it against your velocity or your speed in meters per second, you get a curve, and that curve follows that Maxwell-Boltzmann distribution. It's the speed times e, speed square, times e to the minus e, that's the kinetic energy, divided by kb times t. This is for one particle, okay? And this would be the distribution of speeds that the one particle could have if we follow it. And that means this is a pretty slow speed here, pretty low speed, and this must be a pretty cold gas, okay? Or a very large particle. That would be also possible. So, and we could have, so we have, this would be a low temperature situation, or we have a high mass here. Now we compare this with the higher temperature situation. You see the distribution of speed goes more towards higher speeds. The maximum is now here compared to here, so the distribution it goes to higher speeds. And you see especially here, there's a lot more distributed with higher speeds. And the root mean square speed is not essentially the center, it's here on the side, but just for completeness, this would be the root mean square speed. And with this, you have now a high temperature situation or a very light particle, okay? This is how you get these distribution of speeds. Now, remember when I exploded these balloons and I did all kinds of other explosions where we needed a little bit of energy to get over that activation energy hump? Remember that? Now, this explains this here. Because if I give it a little bit more energy, you see the distribution of speeds increases. It goes more to higher speeds. And all I need is a little bit of a higher speed molecule. That means it's higher kinetic energy. And with this, I get the reaction started, and then the reaction liberates energy, in the case of our balloon explosion, to make water. Hydrogen and oxygen made water, and then it can continue that reaction. This is what it was all about when we added a little bit of energy to it. We got a couple of molecules at higher speeds, at higher kinetic energy, and with this, we got the reaction started. So this is the Maxwell-Boltzmann distribution of velocities, of speeds, and this is the distribution is proportional to v squared times e to the minus e, that's the exponent here, exponential function. E is the kinetic energy divided by the Boltzmann constant times t. So now comes the big question here. We have the distribution, the Maxwell-Boltzmann distribution of, what do we have here? Bromine, okay, bromine. And bromine has its Br2, the atomic mass is about 80 grams per mole of atoms, or 160 grams per mole of molecules, and we are dealing with molecules. So we have, this is our distribution here, okay? And this is 1, 2, 3, 4. So this must be double the speed here than this one here, you see that? So this is our unknown, and I want to know from you, is the unknown X, is that neon, argon, or krypton? Neon, argon, or krypton? So here are the molar masses of those, and now you need to really start thinking. What you need to use is actually probably, you need to use that equation here. And you don't have to do a whole lot of calculation. All you know that the speed has doubled here. What does this have to do with the mass? Okay, what has to happen to the mass for the speed to double? Why don't you think about this and give me your answer? I gave you half the answer already, essentially. It goes from 2 to 4, the root mean square speed. So this is 1, 2, 3, 4. So it doubled the root mean square speed. And your mass is obviously here in the square root denominator. Who is studying physics here? So you know all the answers right away, don't you? Hopefully. Very good. Is that boring for you, that class? It's boring for you? Oh, sorry. Huh? What? What was that? You did? Okay. So how about now? You did good? Excellent. Sorry for being boring, but I have to put the bar for the others also that they can jump it. Okay. These physicists, huh? All right, so there's a distribution here, and the distribution is pointing towards B. Not totally clearly, but it's pointing towards B. And why don't you discuss this with each other and try to find an answer that is the right one? Come on, discuss it. Can you imagine these physicists tell me that my lectures are boring? I love it. But it's all relative.
The lectures are boring.
See? One person spoke up for me. But I opened myself wide up for this, so serves me right. They learn all this in physics. That's the whole point. Okay, let's see what the answer is. All right, let's go with B then, huh? Of course, that's the square root. So the mass has to be 1/4, okay? If you have a doubling of the velocity, so if the mass is 1/4, what would that be? So this would be bromine, and it's this double. That's 2 times the velocity of bromine. What would that be? We put this in here, that would be bromine, okay? And so we need to have 1/4 of this. The fourth would go in here. That would be twice the speed. And what was it then? 1/4. Bromine was 160. Argon is monoatomic, so it's got to be argon. Huh? Oh yeah, it is argon. Okay. I'm going to show you a little demonstration. That's nothing that's going to be explode. If you could have the Elmo up there, please. And I'm going to show you a distribution of speeds now of different size of particles. You see, this is a huge particle up here, so huge that it barely moves. They are bigger particles. These are bigger, and these are smaller. Now, if you can, just keep watching one, okay? I'm not kidding. Keep watching one. It will go very fast, and suddenly it will stop, and it will go fast. This is how we get to these average speeds, okay? See that? This baby is hardly missing. But if it would hit the wall, then it would exert the same pressure, okay? See them here? So if you look at, for example, let's see one. Where do we have one? There it is. And then suddenly it moves like crazy. Okay? So there's a distribution of speeds. And you can follow each of them and you get that distribution function. Okay? Okay, see the bigger ones? Let's see if we get a bigger one stopping here. Wait. I'm getting drunk, okay? I wish you good luck for tonight, and I see you on Wednesday. Thank you, Karen.